which would correspond, if we added those together, let's make a common denominator here. This is, epsilon is another way of saying kappa epsilon naught. So if we added a common denominator over here, we would look at we would see something that looked like, what does this give us? Kappa, or I'm sorry, let's simplify this. It would be D kappa plus 1 divided by 2 kappa epsilon naught A. And this would be the inverse of the capacitance, of the net capacitance. So in these terms, I put it this way just to make this math here a little bit easier. But if we solve for the net capacitance in terms of these, again, the assumption is the same distance of separation, and therefore, and the same charge, and the same surface area. What would this give us for a net capacitance? Let's see, what would we have? We have 2 kappa over kappa plus 1. And everything else would be what? Epsilon naught A over D. What is this? Could this be if I just took this piece here out of it for a second? This is an air-filled capacitor with a total separation distance of this plus this, which is kind of like a separation distance of here to here. If I call that the effective or the net kappa, I don't want to keep using that, then everything else does not change. So it's a capacitor. So this type of a capacitive arrangement still looks like a regular air-filled capacitor, or I'm sorry, a regular parallel plate capacitor. The difference is you can summarize everything inside of here as a single quantity, at least for a parallel plate capacitor. And the effective or the net dielectric constant should be 2 kappa over kappa plus 1. The assumption is they're the same separation distance. If they're not, then this 2 would be a different number, because we had a 1/2 and it's an inverse 1/2. Which means we could treat this thing as a single kappa net capacitor, where this kappa net, for our case, kappa was 2.94. Is that right? That was the dielectric. So we would have basically 5.98, not 98, 986. Yeah. 88, 5.88, yeah. 5.88 divided by 3.94.
Where did 3.94 come from? Oh, okay.
3.94 plus 1.
1.49.
So this would be the effective dielectric constant for, at least for in parallel plate capacitors end to end of the same separation thickness, but this dielectric constant for one and not the other. Now, this being said, what does it say about E and what does it say about V? What is the voltage across either capacitor? And what is the electric field across it? And for that matter, what is C, or Q? Excuse me. Now we can come back over here and say something about the entire picture. First of all, what is C net? Or C effective, C equivalent, there's a bunch of different language, but since you're already used to engineers using different names and language than physicists, I'm just going to use net instead of equivalent. We've got all the numbers to plug in, so it's basically an air-filled capacitor of length, of width D times 1.49. And I erased all that information, so I have no idea what that value is, but
What was our area again?
what's that?
What was our area?
Let me calculate, 0.25 squared.
Yeah, 0.0625.
So,
The separation distance was
4.5 times 10 to the negative fifth, I think.
Just make up a new one. That's fine.
are you sure for the air-filled one? I thought it was a third of that. 1.5. Or 1 point, yeah, isn't it about 1.5? For the air-filled, not the dielectric
What are we talking about?
capacitor. Maybe you're multiplying everything all together on me again.
No, he was asking what the separation distance was, that's the number.
Oh, okay, so, I don't have any other numbers, so I didn't bother to write them down. What was the air-filled capacitor calculation from previous? So we have net times C air from previous example.
2
3.6 times 10 to the negative.
Okay, so it's about 1.49 times 3.6 times 10 to the negative 8 barons. So it's going to be about 1.8.
I've got
after that.
1.83 times 10 to the negative 8.
That's what I got.
I don't know what you just got.
No,
No, it's for the answer.
Yeah, it's
For the answer to that.
Yeah.
you said it's gonna be about 1.8 and we were pretty much right.
Yeah, okay, so what was this number again?
3.6, wasn't it?
Well, 1.5 times 3.6 is not gonna be about 1.8.
Is that what you had?
No.
What did you have written there a second ago? I don't remember what it was.
3.6.
This is gonna be about 5.4 times 10 to the negative 8, as written. I have no idea, you gotta give me some numbers here, because I haven't written anything down that race.
I'm just saying, using that right there,
Oh, you redid the whole calculation?
yeah, using that, I've got 1.83 times 10 to the negative 8.
Okay. 8.7 when you multiply them all together. Is that right? Oh, great, I'm gonna have to calculate. Oh, you guys are not helping me here. So we got 1.49.
7.
And then we've got 8.85 times 10 to the negative 12. It is 1 point.
Well,
Not 1.7. That's epsilon naught times 0.01625.
There's no 1 in there.
0.0625. There we go. Divided by 1 point. What did I say? 4.5.
4.5 times 10 to the negative 12. And this calculation is where I got my 1.8, so.
Okay, so is that then a reasonable estimate of the total? That's 1.49. You're saying your answer, the final answer, or you're
Yeah,
saying that
my
this
final
answer?
answer is 1.8. That's what I was trying to say all along, and why I've been.
Well, because you've got, there's calculations all over, and I was trying to get, what is this value? And then you kept saying 1.8, it's like, no, I don't think so. That's, okay. Is that consistent?
yes.
Okay. I left out my units for epsilon naught. So what is Q? And what is the V and the E across each capacitor? What's that?
Q equals
What are
F
the
times
Q
the voltage.
values? What is Q? What is delta Q? And ultimately, what is? I don't know, that's what I'm asking. If they're the same, the numbers will flesh themselves out. If they're not the same, they won't.
Yeah, yours is the same. Yeah, that's good. Distance is the same.
Okay, so Q's are the same.
Yeah, the Q's are the same.
Q's definitely have to. So Q, then, if we were going to calculate it, would be C equivalent or net times the total V, which is 25. So 1.8 times 10 to the negative 8 farads, 18 nanofarads times 25 volts. So it's 40.6 or something.
4.5.
Yeah, 4.5, yeah.
I said 4.6 times 10 to the negative 7. Oh, if it's 5.8, whatever. We're among friends. Okay, and what is delta V1? And delta V2?
Distributes.
We know what Q is, we know what C1 and C2 are. Or do you need to know?
We do.
So if you want to C1.
Yes. What was C1 in this case? Did we ever calculate it?
C1 was the air.
It's not the same air though, it's half.
Yeah.
Because, or it's not half, it's twice. Right, because the separation distance is narrower, so it's gonna be twice.
C over 2 epsilon naught A.
There's some.
So to get delta V1, we would take Q over C1, which should be Q over 2 times the previous C air. So I'm gonna say C air previous because I don't wanna have to redo all these damn calculations again. And we know 1.8, 4.6, excuse me, times 10 to the negative 7 coulomb divided by 2 times 1.2 times 10 to the negative 8. Is that right? So we're taking 4.6 and dividing it by 2.4. So it's going to be, what is that? 18. Give or take, 16, 18. Oh, damn. And the other one, delta V2, we could either calculate it by taking 25 minus 19, so it should be about 5. 6. Or we could say 1.8 times 10 to the negative, I keep doing that. 4.6 times 10 to the negative 7 divided by 2 times C dielectric previously, which was 3 times this, or about 3.6, 3.5.
So they're moving a little fast for me.
And it works out to about 6 or so, give or take volts. I just took our previous C1 from the previous example, but I didn't want to write it because I know that's going to look more confusing, so I just said I calculated it.
Also, we had the original 25 volts, we got 19 now.
So multiple ways to solve it, if you will. This guy here was the original C1 from the very first example. Or you calculate it for yourselves. So, okay. So I'm not trying to be confusing on that, but that's what it would be. Now, what does this say about the electric fields? Are they the same? Same Q. Well, I don't care about the Q. We've got different voltages across the same separation distance. So they're not the same. You cannot simultaneously have the same charges on each of the 3 interfaces, if you will. The equivalent polarized charge here, and this charge, and this charge cannot be the same over the same distance when you have different voltages in each region. When you have sandwiched or series capacitors, you have the same charge across all of them. When you have parallel connected or side-by-side sandwiched capacitors, then you have the same voltage across them and different Qs. So series, same Q. Parallel, different Q. And those are the keys to how we approach the problem. Now, one thing I will say, do not write this down and save it. Unless you understand, I mean, you write it down because it's the problem that we solve, but do not write this down on your note card as a particular equation, because the only assumption of this was that this was air and this was something else. If this were a dielectric constant of 3, and this were a dielectric constant of 4, this would not be valid. If this were not halfway separated between the 2 faces, this would not be valid. So it was valid in a particular case of one air-filled region and one dielectric region with the same width or thickness. So it's an important thing. You would have to apply it individually to a different problem if you were going to take that approach. And I know this, and I put that in there because I know how you engineers want to work. You get those working equations. Nah, not in this case. This is a very specialized solution.
Okay. That's why this problem
Had
is
we not lost some time here and there, I probably would have had you guys do the same problem with a different dielectric in the top and different separation distance, just to elucidate the differences. But so just please be careful of that. I don't want that to accidentally show up and you use it and you forget that it's only in one case. Okay? So have a good afternoon. Fun stuff.
Next week.
It's all about charge separation, Dan. All about charge separation.
I really
That was interesting
Yeah, something like
seeing
that.
this.